All right, so let's summarize what we learned about Maxwell's equations. So let's consider our scheme hat as we've done before. So this is, let's say, line gamma, and that's our scheme hat. Great. So this is our surface capital sigma, which bounds a regional space, capital omega, and this one is a generic line gamma, and eventually any, for example, this surface here, which stems from gamma, we can call it capital sigma gamma. And again, capital sigma is the entire piecewise smooth regional space, which comprises both the sigma gamma and the hat itself. All right. So what we wanted to study here was Maxwell's equations. EQS for equations for the electrostatic field E. Okay, great. This, of course, needs some charge density ρ, which generates the field E. The first approach to study E was to consider here the most generic type of case for Maxwell's equations, which is the integral form. All right, so how do we write down the integral form? The integral form tells us that for each line gamma in this space, the circulation along gamma of E dot T dl has to be equal to 0, irrotational property of the electrostatic field. Similarly, it tells us that for each surface capital sigma tilde, which includes or is equal to the surface sigma prime, capital sigma prime, which bounds this charge density ρ. In this case, we know that the flux through the closed surface capital sigma tilde of E dot NdA has to be equal to 1 over epsilon naught, the volume integral in omega of ρ dV. Or if you want, the total charge divided by epsilon naught containing this regional space. This is the integral form of the rotational property and Gauss's theorem, right there. Great. The rotational PR for property and Gauss TH for theorem. Excellent. Another case, another way to express Maxwell's equation is in local form. But when? So let's suppose that we want to write here our local form, case 1. In order to write local case 1, while this is always true, this is always okay to do this. Here, we need to have ρ to be continuous, and in addition, it has to be limited. So occupy the finite regional space, cannot go to infinity. Under these conditions, this is enough to be able to write down the differential form, which is case 1 from Maxwell's equations, which in the case of the rotational property tell us that the curl of E has to be equal to vector 0, and the divergence of E has to be equal to ρ over epsilon naught. Again, we have rotational here and Gauss's here. right there. This is called a differential form. Obviously, the differential form is a subcase of the integral form because you need to fulfill this condition in order to use it. So it's not always true. You cannot always use it. If you cannot use it, and yet you want to represent Maxwell's equations locally, the local form case 2 is what you need, and this, we require it down here when this is local case 2. This, we require it when, for example, we have a surface density on a surface capital sigma. So this is capital sigma with whatever small sigma on it. So we have nothing, something, nothing again. In this scenario, we need to use case 2. And in this case, these two equations become quite simply the following. E1, where 1 is this region below here. This is region 1, for example. This is region 2, okay? I can define whatever I want for region 1 and 2 as long as I'm consistent. So if E1 minus E2 projected along the unit vector n, normal unit vector, and religiously we need to go from 2 to 1, which means this is my unit vector n from 2 to 1. Note that in all the proofs I've done in the previous videos, I had 2 here and 1 there. It doesn't matter as long as you're consistent with this choice of 2, 1. Doesn't matter at that point. That's what I mean on purpose on the contrary here, because it's the same thing. As long as you go from 2 to 1, the normal components of V are discontinuous. According to Gauss's theorem, the discontinuity is sigma over epsilon naught. Very similar to rho over epsilon naught, but in 2D. Similarly, the tangent components, so projecting E1 minus E2 along T to 1, then I get 0. So they are continuous. And again, here we have Gauss's up here and the rotational down here. Okay, we also briefly discussed about a case 3, which is when we have something and then nothing, like a hard sphere. I will not summarize it here. What is the key of all this is that already after a few videos, we were able to write down Maxwell's equation for the electrostatic field, in statics, that is. So then eventually in 342, we are going to extend them to the dynamic case. So I know that people have lots of problems with this case too, and so I really urge you to think and discuss in Piazza among yourselves a lot about the case of a shell of charge, a charge shell, okay? As well as the case of an infinite charge plane. Usually, in my experience, understanding clearly what happens in the case of these two examples, you should be able to understand, to grasp the meaning of this discontinuity and continuity of the normal and tangent components, respectively, of the electrostatic field, which again is case 2 of Maxwell's equations.